Here in this video, I'm just going to explain what you should add or what you should include in your lab report, which is on PAT-assisted crystallization. In fact, we performed a crystal growth experiment, crystal growth of paracetamol in its pure solution. So you need to write a report based on the experiment that we performed, and then at the end of your laboratory report, you have to include a separate chapter. So that one we can call it as assignment. So you have to include so this should be your first page. So that's your lab topic, like process analytical technology or PAT assisted crystallization. So this is what we performed in the lab, crystal growth of paracetamol from its pure solutions. In fact, we used isopropanol and we used pure paracetamol, and then we crystallized this particular compound from its pure solutions. So that's the whole experiment. So you need to write a report, and this will be the title of your laboratory report. And then once you finished with your lab report, you have to move on to your assignment topic, which is nothing but you need to give an overview about the process analytical technology, PAT. You can copy paste a few sections from the lab report, especially for your introduction part, and then but try to avoid repetitions from lab report and also in your assignment. So anyway, I gave some instructions in this document. Just stick to this, and then it will be easier for you. And then you have to put your student name, add your student number, and just mention the number of words. I set a limit of 6,000, but if you go more than that, for me it's okay. And submission date, I already mentioned about this. And if you are submitting before the submission date, add your submission date here, or no matter whenever you submit, just add your submission date in your report. I'm going to open the folder in Sulis, so you have to submit your assignment and any other report like a lab report, everything through Sulis. And this document should be one document. This both PAT assisted crystallization and also PAT overview, both should be submitted as one single file. So that's your topic. And just to begin with an abstract. Yeah, I didn't add abstract. I can add right now. Just add abstract like what the experiment is about. So what your experiment is, crystal growth of paracetamol, and we are growing that paracetamol crystal from its pure solution, and we prepared that pure solution by dissolving pure paracetamol in isopropanol. So if you want, you can state the abstract like a crystal growth experiments were performed at 20 degrees centigrade, and then our studied compound is the paracetamol, and using isopropanol as our solvent. And for this lab, we studied like effect of seed loading on the crystal growth kinetics, and then we integrated a crystallization unit with 3 different PAT tools, FBRM, FTIR, and PVM, and so on. And then try to add one line about the conclusion in your abstract. State something like from this study, what we observed is like effect of seed loading doesn't have a big effect on the crystal growth kinetics. In fact, our results were like something deviate from the expected ones. Yeah, so I will explain that what's the observed result and why we call it as it deviates from the expected outcome. So that's one condition. So just to include maybe 4 or 5 lines in abstract is enough, or even 3 lines is enough. Like I did this crystal growth experiment, that's my at 20 degrees centigrade, and these are my system, and the whole process is assisted by PAT, and then the results shows that the effect of seed loading is only marginal on the crystal growth kinetics, something like that. So you can make your own words. And then in introduction, talk a bit about crystallization. I think we already covered enough in this topic during the I think I uploaded a lot of videos. I think part 1A to I think part 1, I have 4 videos, and then part 2 and 3, and then you have also part 4. In part 4 you have 2 more videos, so it's a lot. So talk a bit about crystallization, how it's used as just say it is a purification technique, where it is used, and what are the main advantages of crystallization when it compared to other unit operations like distillation or extraction, and so on, and talk a bit about crystal growth and nucleation, and when we go for crystal growth, when we go for nucleation. Obviously both we need it for purification of some compounds, but still state it in your introduction, and then just talk a bit something relevant to your module. So why crystallization is considered to be an important unit operations in pharmaceutical industries. Yeah, there are 1000 reasons you can find, but try to put it in a put it briefly, like whatever you understand, whatever you think. Okay, I think crystallization can concentrate only the pure compounds from a solution. If your solution contains say like 100 gram of pure compound, and you have only 1 gram or maybe even less than 1 gram of your impurities, then crystallization is a very powerful technique. Yeah, so it can concentrate only your pure compounds. And crystallization also works, you start from a crude material, say 100 grams. Out of that 100 grams, say 30% is your impurity, say like, which means 30 gram. Even when you have extremely high level of impurities, and still crystallization will work. Crystallization still can produce relatively pure product. So that's the main advantages of crystallization. It's relatively flexible irrespective of your impurity concentration in your starting material. So this is one of the main advantages of crystallization. Yeah? And obviously the experiments are so easy to perform. Yeah? So it doesn't require like a highly skilled labor or a high level of expertise. If you know basics of crystallization, and if you know solubility data, then anyone can do this experiment. It's very simple and straightforward. So try to include all of these things in the introduction, and then give some examples where crystallization is used to purify some pharmaceutical compounds. Yeah. Say like paracetamol itself is one example. There are many you can find in the literature. So try to add 4 or 5 examples. You don't have to explain, but just to tell crystallization was already used in the fire, like to purify this compound, that compound, and just put the list them, and then go to the theory part. This is really important. You need to know what is solubility, because nobody can talk about crystallization, crystal growth, nucleation without talking about solubility and metastable zone width. So that's why we have this section in the lab report. So this is something like some theory that supports your experiments. So there are few experiments that we cannot design without having a knowledge about some concepts. So in crystal growth, whether you perform a nucleation experiment or a crystal growth experiment, you cannot start the experiment if you don't know what is a solubility, what is a metastable zone width. I already talked about this in the lecture time. So try to draw those graphs, and then add the graph, show where is your solubility line, what is a metastable zone width, and so on, and then try to explain how solubility changes with temperature, what's the importance of a metastable zone width. So I think that should be enough. So you must add this section, and try to add wherever if you want to add some figures, if you think okay, this is a good place, I can explain this particular section with 1 or 2 more figures, just include the figure. Yeah, that will make my job easy, and then try to, so I can understand where you are going in your lab report. Yeah, so in both in your assignment and also in your lab report, if try to add as much as figures you can. Yeah, like so figures can only improve the quality of your lab report and your assignment. Instead of just writing like crystallization is super good, all good, everything fine, you can add even an image of a of a crystallization unit, like how a batch reactor looks like and so on. And so there is no limit for the number of figures or tables that you want to include in the lab or in your assignment. And then talk a bit about supersaturation. Supersaturation is a must. If you don't know what is supersaturation, no matter how much you know about crystallization, if you don't know to define a supersaturation, which means you know nothing about crystallization. So talk a bit about supersaturation, define a supersaturation, and how it differs from your solubility concentration, and how you can express supersaturation, give the units of supersaturation. So one way to express your supersaturation is delta C. I already showed you in the part 4A or 4B. So try to include that one here. And another one is the supersaturation ratio. This is just a concentration of your solute divided by the solubility concentration. And why we need to have a supersaturation, first of all. This is a very basic question, but still you should answer it. This is a must. Yeah? If you are talking about crystal growth, in general, any topic in crystallization, you should know what is supersaturation, solubility, metastable zone width, and so on. And this is one question for you. You have to answer it. So just imagine you start an experiment with a supersaturation ratio of 1.2, and then you do some experiment, and then you do another experiment with the initial supersaturation of say 1.4. So what will be the effect of initial supersaturation on the crystallization rate? So by the way, crystallization rate is something like how fast your crystal grows, or if you want, how fast your supersaturation is consumed. Yeah? So that's the meaning of crystallization rate. So what happens, like I already explained the theory, but I can quickly say it. Like imagine you start how to do that. Maybe I can open some PowerPoint. Just imagine like you started from a, how to change the color. So I'll just quickly show what I'm talking about. Imagine you start some experiment with say some experiment with a supersaturation of say like 1.2. Yes, is equal to oh, this is going to be nightmare. Yeah? I will try to. Okay, forget it. I think it's better I prepare a separate video just explaining what will be the effect of initial supersaturation on the crystallization rate. And then I will link with this video, and then move on to your experimental section. So this will be the slightly toughest section for you, because I showed you how to perform the experiment in the video, but you have to write it here. You have to write how we perform the experiment, and if you feel this is very difficult for you, or if you need some help, because I did the experiment, so this is something like a virtual lab, and if you don't know how to frame the sentence or how to write the protocol, ask me. I will explain you. So but I expect you to write by yourself, like how many grams of paracetamol we added, what's the reactor volume, or if you want you can say like what's the volume of the solvent, in this case isopropanol. So we added 750 milliliters, and we added I think somewhere around 64 grams of paracetamol, I think 64 or 68, not sure. Check the values, or maybe 76. Check the video part 4 and part A to know how many grams of paracetamol we added in 750 ml of isopropanol solution, and how we created the solution, how we created the supersaturated solution. We did this by heating the solution to to I think 20 degrees above the working temperature. Our working temperature is 20 degrees, and then we wait at that temperature 20 W plus 20 degrees centigrade for almost for 1 hour, I think, and then we cool back the solution to the working temperature in order to create a supersaturation. And once we generated supersaturation, we seeded the crystallizer with 50% of seeds in the experiment 1, and in the second experiment we repeated the same procedure, but in the second experiment we used 80% seed loading. So these are the so we perform 2 experiments, and everything is at same experimental conditions, like your initial supersaturation is same, your agitation speed is same, which is roughly around not roughly, exactly at 350 rpm, and your working temperature is 20 degrees centigrade. And then the first experiment, your seed loading is 50%, and your second experiment, your seed loading is 80%. So explain everything in this experimental section. Yeah? So just to say, the mass of paracetamol added to the crystallizer, volume of solvent, in this case isopropanol, how we generated the supersaturation, and then just also mention the entire crystal growth experiment was monitored and was completely assisted by PAT tools, and then list the PAT tools like FBRM, FTR, and PVM. And I just put this note, so this may be slightly tough. If you have troubles, obviously you can ask me. So just a reminder, we did 2 experiments. So I already said this, 50% seed loading, 80% seed loading, and then write the formula how the calculation should be performed. You can write it on your paper and you can scan and attach it here. Yeah? Like calculation in the sense like how we calculate supersaturation, or how we calculate, the solubility of paracetamol at 20 degrees centigrade. So so from that you know the volume of your solvent, which is 750 ml. So based on these 2 values you can calculate, and the experimental condition, which is your initial supersaturation. In our case, I think it's 1.8 something, sorry, 1.18. So from that you can calculate the amount of paracetamol that we need to add into the crystallizer. So try to use those formulas and then explain me. I already solved it in the part 4a, I think. So repeat it, write it clearly, and then scan and upload it here. And then finally go to the main topic, which is a PAT. So just to give a brief introduction about what's PAT, and especially why it's so important to implement in pharmaceutical industries, and tell the key benefits here. So this will be like a second introduction within this laboratory report, and then what are the benefits, and there are few limitations that many industries cannot easily implement PAT. The main reason is they're really expensive, and it also requires a trained personnel. Yeah, so even after they install, they need someone who knows how to operate the PAT tool. Yeah, so that's why you are learning this. So at the end of this lab report, you can consider yourself as someone who is trained with at least 3 PAT tools: FTIR, FBRM, and PVM. Obviously, it's to get full expertise, you need to work with these instruments at least for 1 to 2 years. But like being an undergraduate student, I think this knowledge is more than enough. Yeah, so you know all the basics. At least you know how it works, how to open the software, how to perform and design an experiment in iControl software, how to control the system, how to monitor the process parameters like your concentration and also your temperature, agitation speed, everything online using some graphical user interface. So at that level of knowledge is more than enough for this module. And also explain the 3 different PAT tools you used and include their working principles. And if you want to add an image for everything, like when you talk about FBRM, what we are measuring is a chord length distribution. It's not a particle size distribution. I already explained this in the part 5a. So what you can do is like you can download some of the images which you can get very easily, and then explain the working principles of FBRM. And also for FTIR, you can get some images and then explain the working principles of FTIR, like and then also for PVM and for all the instruments that we used in the lab, like FBRM, FTR and PVM, you can get their images and from the Mettler Toledo web page. And Mettler Toledo, they even have like 1 minute, 2 minute videos explaining the working principles of FBRM, FTR and PVM. So you can use those information while writing this section, and you can even give a reference to the YouTube links where you learned something about the working principles of these three techniques. Anyway, I already talked about this in part 5a, how FTIR works, how the FBRM works, and slightly about their working principles. So try to check that one. And then we performed all the crystallization experiment using Optimax reactor, and you can get the image of this reactor from the Mettler Toledo web page. In fact, we used Optimax reactor, I think 1001. So add the images of all the pad tools in your report. It's really important. And then, as I said, like whenever we are talking about the working principles, it's better to add images, because images can explain better than 100 words. So, and then we used FTR to monitor the concentration, and then FBRM to monitor the particle counts, PVM to capture the images of the crystals, and time to time to check like how the shape of the crystals looks like inside the crystallizer. So these are the 3 pad tools we used, and we used it for some specific reason, which is already explained here. And then the 3 softwares that we used are PVM, FTIR, FBRM, and the reactor. We control the reactor using iControl software, and all the results from PVM, FTR, FBRM and iControl software, they can be exchanged from one window to another window. So that's why I talked a bit about this data management aspect. So try to include like how data management is easy while implementing, or with easy with PAT. So that's one of the main advantage of PAT as well. And then what we measured is like we just measured the intensity using a FTIR probe, and then we converted the intensity into concentration. This is the formula I used. So like this is the concentration of your paracetamol. This is your initial intensity. This is your intensity at any time t, and then this is your initial intensity. This is your final intensity. So multiplied by C0. So how to explain this? Maybe I try to draw this on a PowerPoint. So what do I mean by this is like let me go to some PowerPoint window. So what we did is like how to delete this. So we have a reactor, and then we have some FTIR probe here. So with FTIR probe, we will have some IR spectra, something like that. And then, so we measure only one particular peak. I will send you an email what's the wave number of this particular peak. I forgot at the moment. So, and then what we do is like you have time, and then you have the intensity of this particular peak. Some particular peak, it has a unit of centimeter inverse. It's called wave number. And then say like at time t equal to 0. So you have a crystallizer, we heat the solution, and then we cool back to 20 degrees centigrade. and then we add seed. So this is your time t equal to 0. Say like, so this is your initial intensity, I0, when time t equal to 0. So this is the time when we added the seed into the crystallizer. So once we add the seed, what happens? So you have your seeds inside. These are your crystals. So these crystals will start to grow. They start to grow, and that's happened because your paracetamol will move from solution to your solid surface due to the supersaturation. Yeah? Supersaturation is the driving force. So, and this process will continue. This process will continue until the solution reaches to an equilibrium. So we can monitor. What we are doing is like, we are not monitoring the concentration. No, what we are monitoring is the IR intensity. What we are monitoring is the IR intensity. So and also, so during this growth process, so your paracetamol concentration is going to decrease in the solution, so which means your IR intensity is going to decrease. So say your IR intensity says like 0.35 or time t equal to 0. So that's the rule. Your IR intensity, concentration of your paracetamol, they increase linearly, something like this. So if your concentration is small, your intensity will be small. If your concentration is high, your IR intensity will be high. So what we are doing in the experiment is like, we add this FTIR probe, and then we monitor the IR intensity. Say you started from 0.35, it will decrease. It will decrease with time, and that's happening because your crystals are growing. Your crystals are growing. It will become bigger and bigger, and then eventually it will reach to a saturation. So this is not even correct. Yeah? So imagine you start from 0.35, it will come down like this, and then it will reaches some constant. So which mean your solution reached the saturation concentration, or in other words, all your supersaturation is consumed. So we start at supersaturation ratio of 1.2. So by this time your supersaturation will be equal to 1. Yeah? So that's how IR works. So what we have is like, so now we have, so once you finish the experiment, let's go to the next page. Let me create a new page. So I use this formula to convert your intensity into concentration, and so these are the values. So you don't have to worry about this at the moment, because it needs some bit of expertise here to convert IR intensity into concentration. So just to use this, just to mention we get the IR intensity from the experiment, and then we converted the IR intensity into concentration. concentration, and so I just mentioned like what are the units of I0, IT. So these are like arbitrary units. So just to mention, just include this formula in your report, and then just to mention C0 refers to your initial concentration, like grams per 150 ml of your IPA, and then the mass crystallized at any time can be obtained using the same formula. So all you need is to apply is like the mass crystallized at any time, that's equal to this value minus T multiplied by the theoretical amount of mass that you can crystallize in the solution. So this should be equal to C0 minus C star. So this is your initial concentration minus your solubility concentration. And then we can calculate supersaturation using the formula C by C star. So if you know the concentration from here, if you calculate the concentration using this formula, and we already know the your solubility concentration, so which means we know the supersaturation ratio. So these are the formula we need. And then if we have initial concentration, if we know the concentration at any time, and if we know the volume of the isopropanol solution or solvent we used, and if we know the mass that we crystallized, then we can calculate the mass crystallized onto unit mass of seed crystals. So I already explained this in part 4a and 4a and 4b, I think, I don't remember. Check that. And then this is the formula we need. I know these are very, it needs a bit of expertise. It's not straightforward to do all these calculations. So we get C from the, in fact you get only IR intensity from the experiment, and then we have to do a lot of data manipulations to convert them into concentration. So anyway, I did this already for you. So I'm going to give the data to you. So it will be in an Excel sheet. I even plotted the results for you. And then FTIR, so FBR, I'm sorry. So your FBRM will measure the chord length, so we don't need any post-processing of data. So we need all this, we need to convert your intensity into concentration only when we are dealing with FTIR. But if you are dealing with FBRM, practically we don't need to manipulate anything. Yeah? So it's very simple and straightforward. So whatever the data values that we get from FBRM, we are going to plot it straight away on the Excel sheet. And then PVM are just microscopic images to get some idea about the shape of the crystals, to check is there any events like whether your crystals are agglomerated, or maybe whether we observe any broken crystals. So these are the main advantages of PVM. So obviously we don't need to post-process anything. So only for FTIR we will get the results in terms of intensity, and it is our job to convert the results into concentration. So anyway, I did that for you, so you don't have to worry about this. And then results and discussion, this is the main part. So you have to write like we performed something like 2 experiments, and then you have to mention like what's the expected results. So the expected result is like normally if you have a higher seed loading, the growth kinetics will be faster. And then okay, what else you need to include? Anyway, the results show the effects are okay. I almost mentioned the experimental observation from the experimental result. So what I mentioned is like I can go back to the PowerPoint. So what I mentioned is like so if you have a crystal, say let's have like we have a supersaturation say 1.18. If you have one crystal, so, which mean, and then you have another experiment say supersaturation 1.18, and then you have two crystals, so the amount of mass, say like at the end of 1 minute, say when t equal to 1 minute, say like say 1 gram of your compound moves from solution to one particle. Yeah, so 1 gram, so how do you say like 1 gram of your crystallizing compound moved from your solution to the crystal side, to the solid side. And then if you do the same experiment with two crystals when t equal to 2 minutes, so you will see what we expect is like 2 gram of compound moved from the solution side to the solid side. So if you divide by, if you calculate the kinetics, so we can call this as a depletion in concentration. Say if you have a probe here, so your concentration, your depletion in if you start say like 5 grams per liter, at the end of your t equal to 1 minute, your concentration will be 4 grams per liter. But in the second experiment, at the end of your 1 minute, the depletion in concentration will be 5 minus 2, that will be 3 grams per liter. So if you check the rate, like a change in concentration with respect to time, so this will be 3 divided by 1. Sorry, this is wrong. This is wrong. So 3 grams per liter. Say let's put say like how do you call like the change in concentration in this experiment should be like 2 grams per minute. That the depletion in concentration in this in this experiment will be 1 gram per 1 minute. So which means the rate is faster here. The rate is faster here. So what we expect from this type of experiment, say you have supersaturation and time. So if we start with one particle, say your supersaturation depletes with respect to time, follow this trend. And then if you start with the two particles, the depletion in supersaturation will be even faster, and then eventually it comes to the same point. This is the equilibrium point. How do you say like? So this is with one particle, and then, sorry. So this will be with one particle, this will be with two particles, and that's because we are transferring more molecules from the solution side to the solid side when we have a higher seed loading. So that's the concept. So in your experiment, we used 50% seed loading and 80% seed loading. So what we expect from the result is something like this will be 50% and this will be 80%. So this is the expected result. But I already did the calculations for you, and I found the results are bit different. Yeah, so it deviates from the expected results. So I think I mentioned everything that I want to say. So let's go back to the assignment topic. So I can even show the results. I already did it for you. So this is the experiment we did, and I already calculated something like here. I already said how the expected result should looks like. %50 seed loading. This is your 80% seed loading. But our expected result, that's our expected result, sorry. But the experimental results looks like this. 50%. And then 80%. So what it says is like when we have the higher seed loading, the depletion in the concentration is slow. Which means slower kinetics, yeah. And normally this can happen, say like the rule is like if you have more crystals, more mass will move to your crystals per unit time. So if this rule, if you cannot expect this observation in the experiment, the only thing that we can imagine is like something happened in the experiment 1, 50% loading. So what I can expect is like so once we loaded with some seed crystals, probably it created nucleation. It created too many smaller particles. We call this as a secondary nucleation. So we call this a secondary nucleation. So mention this in your lab report. Just to mention like we added probably at this particular experiment, probably due to some external disturbance, or maybe there may be some impurities in the solution that can trigger this type of events. So if you have some unwanted impurities, then it could trigger something called as a secondary nucleation, which can give rise to more crystals. So which what it happens is like, so once if we encountered secondary nucleation, so which means the number of crystals inside the crystallizer will become higher, will increase. So what we are thinking is like we have only one particle, but due to secondary nucleation, we might have more than one particle. So in that case, the mass move from solution to solid may be almost similar to your experiment 2. So this is the whole idea, and that's why crystallization is a very difficult process. Yeah, like even a tiny bit of impurity, maybe a dirt particle inside the crystallizer, can create this type of unwanted events. Yeah. So anyway, I don't know, maybe we may be lucky. At least it gives me an opportunity to explain like what could have happened into the crystallizer. Yeah? And also crystallization is very, very important process, but it also need high skills to perform an experiment. Like probably there must be some dirt particle, that's what I expect, and that could have triggered the secondary nucleation. So that's why the depletion in concentration is almost similar, no matter you start your experiment with the 50% seed, and no matter you start your experiment or with 80% seeds. So talk a bit about nucleation, secondary nucleation, and just to tell that this could be one reason. They almost overlap with each other. Yeah? So what you need to say is like the depletion in concentration, depletion in supersaturation with respect to time, they all look similar. And this can be expected due to secondary nucleation in the experiment 1. So just mention it in your report. And then I already made the figures for you. Just include all the figures in the Excel sheet. I can show the image. I think something is not right in this image. I will fix it and then I will send it to you. But just look at the trend here. Yeah, you see it from your concentration is the depletion in concentration with respect to time, with 50% seed loading and 80% seed loading. They're almost the same, and in fact with 80% seed loading, the depletion in concentration is slightly slower than the 50% seed loading, and this is due to the secondary nucleation. Yeah? So probably there must be some dirt or some disturbance occurred during the course of crystallization, and that's more than enough to trigger secondary nucleation inside the crystallizer. So whatever I said, just state it in your report, and also try to read a bit about secondary nucleation. So this is some concept that you will learn through this particular through this particular laboratory experiment. So try to explain what is secondary nucleation, and we expected, or maybe we believe there is some secondary nucleation in experiment 1. Yeah, so try to mention this. So all these images are the same result but expressed in different form. Here it's expressed in terms of concentration with respect to time. Here I mentioned in terms of mass crystallized with respect to time. I already showed you how to convert your concentration into mass crystallized. You have to check part 4a and 4b, and then this is the amount of mass loaded onto per unit mass of your seed crystal. So how many grams of your paracetamol are crystallized onto unit mass of your seed crystals. Yeah. So I already showed you how to get this value, and then this is your supersaturation ratio, how your supersaturation ratio changes. So this is, I think there is some mistake in this graph. Yeah, definitely this is not correct. 1.2, supersaturation ratio should go from 1.2 to 1, and that's it. Yeah? I will fix this one, and then I will send to you the correct graphs. So discuss this observation. Just to mention like why no matter you start your experiment with 50% seed loading and 80% seed loading, the kinetics looks same. Yeah. So the change in concentration or the change in supersaturation or how fast your mass are getting crystallized per unit time, everything looks similar, and that's because there should be some level of secondary nucleation in experiment 1. So mention that in the results and discussion part, and then you can even mention like if you go back to this result, this graph is not correct, but still I will just explain it. Anyway, the trend will look like this. I will fix this and then I will upload the correct file in the Sulis. So one thing you can say is like if you see the mass crystallized, it's very rapid. In the first what's the time here, 2:33. If you see the mass crystallized from time t equal to 0 to roughly around 200 minutes. So it's very fast in the first roughly like first 3 hours, and then the growth kinetics is very slow. Yeah. So try to mention this in your report. That's really important. Yeah? So these are some observations. Just you use your eyes and then you just say like, okay, this is the whole trend. The mass is crystallizing at time t equal to 0. Nothing is crystallized, and then with respect to time, I see some mass is getting crystallized with respect to time. So and then you see like from 0 to 8. So up to 10 gram, you crystallize up to 10 gram. In the first 2:33 minutes, and then from 10 to 12 it takes several hours to to reach the saturation point. Yeah, so just to mention this in your report. If you have any troubles, just ask me. I know this is very tricky, but because you are not used to interpret this type of data, but if you have any troubles, tell to me. Yeah? And then I said to you, like 50% loading, probably we could expect some secondary nucleation, and that is correct. So here I plotted all the results into one graph. You have time here, and you have concentration. Okay, concentration is not correct. I will fix this one. And then I put the particle counts here. So if you see some number, the blue one, the particle count should be, if there is no nucleation, the count should remain constant. Yeah, so let's go back to the PowerPoint. Say like, imagine if you started your experiment with only one particle, when you put the FBRM, the number of particle count should be constant throughout your experiment. It should be equal to one particle. But if something happened, some new crystals formed due to nucleation, then this number will go up something like that. So that's what we observed in the experiment 1. So let's go back to experiment 1. You see the particles which are less than 10 microns, it was continuously increasing during the crystallization experiment, and also particles 10 to 100 microns, you see a slight increase in the number. So we started the experiment roughly, you have to follow this, my arrow. So you have this, maybe I can put some line. So when we started the experiment, the number of particles, so the particles which are less than 10 microns, we started, how to draw this arrow, okay. So just to follow this blue arrow, so what it says is like the particles in the size which are roughly less than 10 microns, the number of counts is 50, 100, roughly around 140, and then for the case of 100 to 1000 microns, the number of particles is approximately 200, and then when we started the experiment, the number of particles is roughly around 310, is 310, yeah. But we see that with respect to time, the number only goes up. So which means this can happen only if there is some nucleation in the crystallizer. So this is a good experiment to demonstrate the power of FBRM. So at least your FBRM helps you to show like how it can pick the unwanted events like secondary nucleation during a crystal growth experiment. Yeah. So you can use this graph, and you can tell like, okay, I look at the FBRM and what I see is like a sudden increase in the number of particles, especially the fine particles and also particles in the range 10 to 100 microns. So explain this, add this in your discussion part. And if you look at 80% seed loading, everything is constant. So how do you see? Let's put this arrow mark here. So particle counts is in this side of y-axis, yeah? And in the left-hand side you have concentration. So if you look, the particle counts remains constant. Everything is constant. The number of particles in the fines and also here all remains constant, yeah. So these are approximately okay, yeah. These are, if you put a line, everything is a straight line. Yeah? This one is approximately constant. This is approximately constant. So this is fine. So in this experiment, there is no secondary nucleation. That's the discussion you have to put it in your, this is the observation you have to discuss in your report. So in the first experiment, we observed a secondary nucleation, and we realized this by looking at the particle counts that we obtained from the FBRM. In the second experiment, practically there is no secondary nucleation. So that's the thing you have to talk in your laboratory report. And then if you look at both the images, I don't know whether the Panopta can capture the arrow. So if you look at both the experiment, you can see like a sudden, like a small increase during the early stage in the FBRM. So let me draw in the So if you look at the FBRM, so you will see some sudden slight increase in the beginning, and then it become constant, no matter whatever the particle size is, whether it's fine, less than 10 microns, or 10 to 100 microns. We see this trend, sudden jump and then followed by constant. And normally that happens because when we seed the crystallizer seeds, the seeds will be together, they will be clubbed together. We call them as like slightly agglomerated, and then once it goes through agitation, it will become into single particles due to the agitation, due to the force, shear force created by the impeller. Yeah, so that's why. So after a few minutes, you will see the real counts. So everything will break and then everything will become into single particles. And this one we can monitor in the FBRM. So at the beginning, say it will be like 50, and then once the impeller break these particles and then convert them into single crystals, so you will get the real numbers here. And then everything will look constant after this point. So that's the purpose of FBRM. So PAT is a very, very important technique. I think you learned a lot through this this laboratory experiment. Yeah, like I can tell what PAT can do, how PAT works purely from theoretical standpoint. But at least now, when you look at the experimental results, you see how precisely it captures what's happening inside the crystallizer. All we did is 2 experiments. And in one experiment, the particle counts remains constant. So I'll just change the line. I just follow the red arrow. So almost constant. Yeah, this can be considered constant. This is constant. Blue is constant, and the violet color is constant. But in this case, in experiment 1, you see the fine particles is roughly around 140 number, and then it suddenly jumped to 250, and then it continues, and then it jumps to 350. Yeah? So which means there is secondary nucleation throughout the experiment, and then it's also 10 to 100 microns. It's also increasing constantly. Yeah? So these are some examples of or if you want, we can say like some key advantages of FBRM. So that's why we implement FBRM in crystal growth experiment. During crystal growth, one thing we don't want to see is like increase in the number of counts. But anyway, in this case it occurred, but we can monitor this during the course of crystallization. In industries, if this really happened, if they observed a sudden jump in the particles number, what they do is like they will stop the reactor or the reaction roughly around 600th minute, yeah, and then they will start to perform a fresh experiment. So these are the key advantages of FBRM, which you learned through this exercise. So include all these points in your discussion part. And then conclusion, yeah, just to mention 2 or 3 lines. So what's the expected effect, and then why the results deviate, and then just mention what are the things you learned through this exercise. This is up to you. You can write anything you want. Yeah? Just write maybe 4 or 5 lines, like what you learned through this laboratory exercise, and then try to answer the following questions. You have this part because I did the calculations for you. This calculation is not right. I will fix them, but I will change. But anyway, I will give you all the graphs to you. I will fix this calculation, and then I will send the results to you. Since I did this everything by myself, try to answer this one question, like we need to crystallize some compound at 40 degrees centigrade. We know the solubility of this compound is roughly is exactly 100 grams per liter, and then try to design a crystal growth experiment, like what will be the mass of API we need to add, or what will be the seed mass that we need to add, and how will you create a supersaturation. And these are our experimental conditions. So we need to grow the crystals at 40 degrees centigrade. Our initial supersaturation is going to be 1.2, and the seed loading is 50%, and then your reactor volume is 500 ml, which means we are going to add 500 ml of your solvent. And then this is the density of your solvent, 786 kilograms per meter cube or grams per liter, both are same. And that's it. Finish the lab report and then go to the, so in fact you need to put some work, especially in conclusions, results and discussion. And then this part, all you are going to is just explain or just copy paste it, and you need to do some work here, and then you have to do a bit of writing here, experimental part. So this you can write this part only if you can understand how the experiments are performed. And then introduction, you have to get some literature data, solubility. You can find something from the literature, I already explained in the videos I posted. So obviously if you have some trouble, you can ask me anytime. Then go to the assignment topic. So talk only put a small paragraph about Industry 4.4 and what's digitization of pharma industry. So if you don't know what is this, I already uploaded reference 1. So go to reference 1 and check what is this about, and then just include that in as your first paragraph. This is really important, because if you are going to work in pharma industry, you should know what are the strategies behind or the goals behind Industry 4.0 and what's meant by digitization. So if you need to advance anything, the current level of state of art towards Industry 4.0, or to digitize our any existing plant, we need really PAT tools. So PAT tools play a big role in taking the existing technology to the next to the next level. So applications of, and then you talk a bit about applications of PAT in pharmaceutical industry. Try to list at least 4 different applications apart from crystallization. So you can get this very easily. Like one is like manufacturing of monoclonal antibodies. I already put the reference, and then what type of PAT tools are used in these different industries or different applications. And under each example, just to explain what PAT tool they used, and then what they actually measured using that PAT tool. And these are few examples that comes to my mind. I typed something. There are many we can find in the literature. So mainly in solid oral dosage manufacturing, and also you can also include something related to crystallization. They use PAT tools to monitor impurities, if there are any impurities in the solution during the course, or maybe like imagine you are crystallizing paracetamol, and suddenly if the paracetamol degraded in the solution, then FTIR can give you such information. It tells, there is something happening in the crystallizer. I see some new compound, probably something degraded inside your crystallizer. So these are some advantages of using PAT, or maybe imagine you start your experiment with a crude product that contains paracetamol and one more impurity. PAT can monitor both the concentration of your impurity and also the concentration of your crystallizing compounds, if in this case is paracetamol. So these are advantages of using FTIR. So mention these things, and then you can talk a bit about Raman spectroscopy. Raman spec is mostly used to monitor the drug loading in the tablets. So that itself already you have 4, I think. So, and then try to, if check the literature, you can find lots and lots, especially in the last 5 years. There are so many papers published on using or implementing PAT in pharma industry for different applications. And then try to, if you take some images from literature, say like if you're talking about monitoring impurities using FTIR, then obviously you can copy paste those images and then tell, okay, these are the images studied by these guys and they monitored this particular impurity, and that's how the spectra looks like. Yeah? So it's up to you. There is no limit for the number of images that you need to paste. And then so at the end, you should, in this section, you should demonstrate like you really understood how PAT helps us in the pharma manufacturing industry. So that's the expectation. And then discuss any 3 other PAT tools which are not used in the laboratory report. You have to explain their working principles in detail, add some figures that can explain the working principles, and then tell what it can measure and how they will look like, the results. So this information you can get it from literature, and also check the book. I uploaded a handbook, check that book. And give references. If you took the information from book, web page, article, YouTube, you must cite them and give the correct references. So you can use any format when you are adding the reference. Yeah, it's up to you. But you should cite. Even if you are watching a YouTube video that talks about working principles of FTIR, for example, put the link of the YouTube video, and I think that's enough for this one. So it might look tough, especially when you are talking about experimental part and the results and discussion part. But whatever you write, that's going to be your learning outcome. So that way it's not a bad idea. At least I will know how much you learned through this lab, and try to put maximum information. If you think this is what is happening and that's what I understood from the result, even if it is wrong, just write it. Yeah? And then at least I give marks for the people who interpret their results in their own way. Yeah? So if they think, okay, I think something is happening, the growth rate is faster or slower, whatever comes to your mind, just write it. Yeah? I think it's enough. I think I covered everything. So try to include whatever I asked in your lab and your assignment. So this is enough. I'm going to stop recording. I just want to mention, I think I did a mistake before, like I used another formula to calculate concentration. So that's a wrong one. So I'm just going to repeat now how to get your concentration from the IR intensity. So using FTIR, what we get is like a intensity that should change linearly with respect to your paracetamol concentration in the solution. So I think I already explained this. So let me go to some new slide. I said to you before, how do we get the concentration from IR intensity? So the FTR which we are adding, which we are integrating with the crystallizer, will give intensity. So you have your time on the x-axis, and then you have your intensity on the y-axis. So this is the value that we get from the IR. So we start from I0 and then it decreases and then eventually it reaches some constant. So this is your final intensity. So which means this will the concentration at this particular intensity will be equal to your solubility concentration, and this is your initial concentration. I think we added something around 76 point some grams of paracetamol in 750 ml of isopropanol. So this will be your solubility concentration expressed in grams per 750 ml. So the correct way to convert this value into concentration. So this is some method that I developed in the lab. So you have I0 and then you have IF. From this we can calculate the mass crystallized at any time. Let's put so this is your mass crystallized at any time. So this will be equal to intensity minus time, intensity minus intensity final multiplied by theoretical. So we know how many grams we added, 76 point something, some grams per 750 ml. We know the solubility value, I think 64 point something grams per 750 ml, I think. So C0 minus C star, that should give delta C theoretical. So once you have that value, let's go to new slide. So once you have this value, delta C is equal to C0 minus C star, then we can calculate concentration from the intensity I0 minus IT, I0 minus IF. So multiplied by delta C theoretical. So this is delta C theoretical. Delta C, sorry. This is this equation is we need to calculate mass crystallized. This is a constant, I0 is a constant, I0 is a constant, IF is a constant. So I0 minus IF, this is a constant. So this one is nothing but you start your experiment. The first value is I0 and then it will reach some constant. So this value, all this value at here, so that will be equal to IF. So both are constants. So the whole denominator is a constant. And then the numerator, initial intensity, this value is a constant. So intensity at time. So this is nothing but intensity at any time that will change with respect to time. So this is the only thing that's going to vary with respect to time, IT. And delta C theoretical, this is your experimental, from experimental conditions you can calculate. This is a constant. So that's the maximum amount you can crystallize in your solution, delta C theoretical. So this is the first step. You need to calculate the mass that you crystallize, with respect to time. And once you crystallized that, let's create a new screen. So once you have that, then you can calculate concentration at any time. So time versus concentration, we can calculate. We started from 76 point some grams, I don't remember, and then it will reach to saturation, solubility. So solubility concentration will be roughly around 64, I think. I don't check the part 4 of the lab report. I clearly mentioned what's the solubility value. So but we don't know what's exactly the concentration. All we know is time versus intensity from IR. So how to convert this intensity IT into concentration at any time? So the formula is very simple. C0 minus delta C. So delta C we already calculated in the previous slide. So in this, so just take that value and then subtract it from the initial concentration. So you have your From that you can calculate delta C. Delta C, from delta C we can calculate your C value. Yeah? So if you plot your delta C will be like this, delta C versus time, and your concentration will be like this, C versus time. So both these equations I used myself in the lab. This is something these are very simple mass balance equations, but it's a very easy way to convert your intensity into concentration. You cannot find these expressions in the textbook or literature, because I think it's simple. I don't want to say I developed it, but this is something I figured it out, to convert your intensity into concentration using a simple formula. So this may be tricky for you. So what I did is like I explained you how to get, you get intensity, you get versus time, you get something like this. So what it says is like if the intensity is decreasing with respect to time, which means your concentration in the crystallizer is decreasing with respect to time, concentration in the solution, and that's normal because your crystals are growing. Your crystals are growing at the expense of the concentration, in fact at the expense of supersaturation in your solution. Your supersaturation are continuously getting consumed, and that's happening because your crystals are continuously growing, and both will stop once once your solution reach the equilibrium concentration. Yeah? So I hope you all understand. So once you have intensity, all you need is just two formulas. Yeah? So let me put a new screen. It's a simple one. All you need is a very simple formula. So C, delta C is just repeating it, IT minus I0 minus IF, multiplied by delta C theoretical. So from this we can calculate concentration at any time, C0 minus delta C theoretical. So from this equation, so we get time versus intensity. So we apply this equation, and then we get a graph of time versus delta C, something like this. By the way, delta C is expressed in our experiments, grams per 750 ml of IPA. And from this we can convert them into, so since we have delta C, we know initial concentration, something 76 point some grams per 750 ml. So just minus 76 minus this value, so you will get something around like this. Yeah. So once you have concentration versus time, we know solubility concentration. You can get supersaturation versus time. So S will be C by C star. So from this graph we can get S is equal to C by C star, something like this. S versus T. And since we have C versus T, from that you can calculate QE, C0 minus C into volume by mass. Yeah. I hope you all understand. Let me make one more slide quickly to show what is this QE value is all about. QE is equal to C0 minus C volume per mass. So what is this value is something like, so during crystallization your concentration is decreasing. Yeah? So you start from C0, say like 10 grams per 750 ml. Say at a time t equal to 1 minute, your concentration is say 8 grams per 750 ml. So QU value will be, just to take the difference between C0 minus C. So what it says is like 10 minus 8. So this is like 2 grams per 750 ml. 10 to 8. No, let me check. 10. Yes, so it's which means 2 grams per 750 ml. So this many gram of your solute molecules moved to the solid side. Yeah? So which means your crystals are growing at the expense of this many. How do you say like? So let me draw some graph. So let's call this as a liquid concentration. Let's call this as a your solid concentration. So what's really happening is like. So initially your solid concentration say is 0, your liquid concentration have some number, say 2 grams, maybe 4 grams. And if your solid gram is 2 grams, which means your liquid concentration should be whatever this initial value minus 2. So you are growing your solid at the expense of your liquid. So that's the meaning of this. So this number 10 minus 8, it says 2 grams, which means 2 grams moved from your liquid side to the solid side. So that's the meaning of this one. So 2 grams moved to the solid side, which means your crystals will be growing. And then you just divided by mass of the seeds. So what it says is like if your mass of the seeds is 4 grams, so when you divide 2 by 4, it means whatever the number you get, that will be 0.5. So which means you moved 0.5 grams of the crystallizing compound into 1 gram of your seeds. Yeah. But what we are moving exactly 0.5 grams per 750 ml divided by something expressed in grams. So if you need to remove this volume, just multiply it by volume of your reactor volume. So that's 750 ml. So both will get cancelled. So eventually you will get some number, grams per gram of seeds. So what this quantity measures is like at any instant of time, like how many grams of paracetamol you moved to 1 gram of your seed. So that's the meaning of QE. So it's a simple mass balance equation. So that's the formula to get it. Yeah, I know the students who do not have an engineering background, they may not know how to perform a mass balance. So that's the basic calculations. It's really simple. So all we are just calculating how much mass is moving to the solid side. So this is expressed in grams per 750 ml. So we multiplied by volume. So 750 ml and 750 ml gets cancelled, and you divide by the mass of seeds. So that one will give you a rough idea like how much mass of paracetamol is getting concentrated onto 1 gram of your seeds. So I hope you all understand. So I will append this video to the one which I already recorded. So just to say that I did some mistake in the formula which I used to convert intensity into concentration. But anyway, don't worry about this. All you need to know is like how to get these values. But anyway, I did the calculation for you because it's a very long, heavy data. Yeah, it's only 2 experiments, but we recorded the experiments almost for 1 day. So I did the calculations because you might do some mistake if you do it by yourself. So I will quickly show what is shown in this Excel sheet. So this is our experiment 1. So this is experiment 1. So we have time. We recorded everything in seconds. I converted it into minutes, just dividing the sec by 60. So you will get into minutes. This is the actual intensity which we get from IR spectra using FTIR pad tool. And then I used the formula. I already said to you how to calculate. So this is delta C is nothing but mass crystallized. Mass crystallized at any time. So I use the formula initial intensity minus intensity at any time divided by initial intensity by final intensity multiplied by the amount of mass that we can crystallize. So this is nothing but DC, delta C. So this is your delta C. So that's our initial concentration. We added 76.048 gram. Follow the highlighter. So we added 76.048 grams per 750 ml of isopropanol, and this value is our solubility value shown in green highlight. So you take the difference between these two, you will get the amount of mass that we can crystallize in 750 ml of isopropanol, which is equal to, I showed it in the orange highlight, so 11.923. So that's the mass that we can crystallize. And I said the first experiment we did with a 50% loading, so which means exactly 0.5 of this value. So that's mass crystallized multiplied by 0.5, that's your seed mass. We have all these values here, and then we have our intensity. This is our initial intensity, the first value 0.364, and final intensity is 0.31825. If we come to the end of experiment, so this is your final intensity value, 0.3185. So from that I calculated the mass that we can crystallize, and from there okay, this column is not necessary, I can delete it. So this is your concentration. So this is nothing but your initial concentration, which is 76.048 minus mass crystallized at any time, which is here in the D column. So just if you double click, you will know what's the formula I used. From that you will get some idea. And then once we have our concentration, we can calculate supersaturation ratio. This is nothing but concentration divided by our solubility concentration. And then from that, and we have concentration, so we have the mass of seed crystals that we added. So mass of seed crystals added is in blue highlight, which is here, 5.9615. Just to follow the cursor. From that we can calculate QE using the formula I already explained. And from that we get the correct graphs also. So these are the correct graphs here. If you see, we started from, let's put an arrow here. So we started the experiments from 76, and then we end the experiment when our concentration is roughly around 64.125. So that's our solubility concentration, which is here. See the green highlight, 64.125, and you see that we started our experiment from 76, follow the blue arrow, and then we finished when the concentration reached the solubility concentration, which is equal to 64.125. Yeah, I hope you all can follow this one. So all I did is like so this is your concentration, and then the same rule applies. Say like maybe I can change it to green or red. Just follow the red arrow. We started the experiment when time t equal to 0, nothing was crystallized. So zero amount of mass getting crystallized, and then when you reach equilibrium, you crystallize roughly around, this should be equal to 11.923. You see that in the orange highlight here, 11. So you start from 0, and then this is the amount you crystallize, roughly around 11.923, around near 12. Yeah. So if you want, I can draw another line here. So this will be equal to 11.925. Check the blue arrow. Yeah. I can do the same here in the concentration plot. If you see the final value, the concentration, somewhere around the 64.125. Yeah. So this is our final concentration. So I already did the calculation for you. So we have our concentration. So I already calculated supersaturation ratio, and I plotted it against time. And then this is plot of QE versus time. So all these images are for experiment 1, for the experiment that we performed with 50% seed loading. So I also already calculated the same for the experiment 2 as well. So I already corrected the error. So this is the correct value. You start from 76 and then you end in the 64. So you both reach the same concentration, and that's because all the experimental conditions are same. The only difference is the seed loading. Yeah? So your seed loading should be 0.8 in this case. So our seed mass will be 9.5384 in this experiment, grams. Hope you all can follow. So this is your mass crystallized with respect to time. Let's show through the arrow. So you see it's like 0 grams crystallized at time t equal to 0, and then you roughly crystallized 11.94 grams. Yeah, so that's the whole idea. I already calculated the solubility ratio, supersaturation ratio, and then the mass crystallized per gram of seed mass, and then I even compared the results for you. So here what I plotted is like, this is from experiment 1, 50% seed loading. This is experiment 2, the right side image. How to use pointer in this Excel sheet, I don't know, just follow the cursor. Yeah, so whatever the image which is highlighted now, so I'm moving the arrow. So this one is your experiment 1, and then this is your experiment 2 that we performed with this is experiment 2 that we performed. You see the arrow here which I'm moving now. So we performed with 80% seed loading. So we performed with 80% seed loading. So you see the seed loading which is here, and so this is your F. In the other side of second y-axis, I plotted FBRM counts. So this green, blue, and violet, they all are FBRM counts. Yeah. So I plotted the results already for you. All you need is to copy paste all these images. So you first copy paste the images from experiment 1, 2, 3, 4, and then try to discuss about the results. And also this is your 50 image, and then go to experiment 2. So plot in here. I compared both 50 and 80% seed loading. So it's okay, you can include all the images. So you will get 4 plus 4, 8, plus these 2 images, 9 and 10 images in your report. So all you need is to copy paste and try to discuss the results. I already explained how to interpret this data. So I already explained how to interpret this data. So try to listen to my video and then give some reasons, like why this particle count numbers are increasing, what could be the reason. And in this graph, like you say, like mass crystallized, they almost look similar. Yeah, like seed loading does not show any significant effect. I explained this based on secondary nucleation. So try to include all these reasons in that discussion part. Yeah. So this report is to show how much you understand about the crystallization experiment. Yeah. The people who do PhD in this area, after 3 years, they think it's very difficult to interpret the data. So I can understand if you do some mistakes, that's okay, but don't copy, don't discuss. Okay, you can discuss with your friends just to know how do you interpret the data, what do you think about this graph. If they have a better understanding than you, they can share their knowledge with you, and then but you write on your own. Yeah, you can discuss with your friends, take the ideas from them. If they can explain you, then you can ask them, or you can also ask me anytime. But when you put it on the paper, it's up to you. You have to write it using your own sense of understanding, what you feel about the experiment, what you think about the result, and that's enough for the lab part. Yeah. So this video I will append to the video which I recorded already. I think that's around 1 hour, so this will be roughly around 20 more minutes. So this will be like instructions for how to write your report and your assignment. So thanks for listening.